Good morning. Thank you for coming to my thesis defense presentation. My topic is about the design and evaluation of a hierarchical OpenFlow SDN control plane. I'll be going over what that exactly means. I have a bit of an introduction. Jumping right in, my goal is to come up with a scalable network control plane that's able to seamlessly integrate multiple service stacks, which are basically network stacks, services. SDN is traditionally good for logically centralized network management, but when it comes to having multiple sources of network control, it tends to become conflicted in that a controller might send conflicting messages to the data plane on misconfiguring switches and routers. So to work off of a point, we take advantage of the fact that some kind of services that are provided by these controllers have different types of requirements from the data plane of the network. So I want to just go over some of the motivations of why I want to have multiple services on the same network. It turns out it's pretty common to have that in modern day networks. For example, we might have shared networks. Multiple service providers may do something called active infrastructure sharing, where they might share the switches and routers and underlying services, but have their own network stack implemented above it to be able to service their own user bases. There's second one, heterogeneous networks. Say even a small LAN in your house or say on a campus might integrate both, say, Ethernet and Wi-Fi, WiMAX, and each of them have different types of requirements in terms of management, security, so on and so forth. And finally, there might be multiple networks that are administered individually, but might be underarching under a overall global kind of policy, like say different campuses with their different networks, but with a global access policy for only students and faculty and staff. So what is SDN? SDN stands for software-defined network, software-defined networking, either one. It's a network architecture paradigm. What it basically does is split the network into three logical components: a control plane, data plane, and a control channel. The control plane is basically the implementation of network intelligence, the management, the protocols, basically the intelligence. The data plane is the simplified forwarding elements that are purely there for moving traffic according to what is called a flow table, which is a map between certain packet headers and certain actions, like say flood a packet out of all the ports of a switch, forward out of one port, drop a packet. And finally, there's the control channel linking the first two elements, the data plane and the control plane, letting the control plane manipulate the data plane using these control protocols that directly access the flow table and manipulate its contents. So the overarching model here is it's logically centralized and it's programmatic. The network logic is run as a program on a, say, like a server or a commodity PC. And it's sometimes referred to as a network operating system and also a controller. And the data plane elements are usually referred to as data paths or switches. And there's the summarizing picture with the three components. So SDN is just a paradigm, so we want to talk about implementation. The one that we want to focus on is referred to as OpenSDN. It basically tries to openly standardize and create implementations of SDN type networks. So it might have different types of protocol libraries and different types of controllers that are openly available, or have, say, software switching implementations. We focus on OpenFlow because it's fairly well known. It's kind of popular amongst research and industry, and there has been many different types of controller implementations, different software and hardware switches that support it, And as a result of research, many different types of tools that ease development, like say data plane emulation and controller benchmarking, so on and so forth. So traditionally, in terms of OpenSDN, the model has been there will be a single physical controller, like a single server managing a whole data plane with multiple switches. In early cases, the controller was monolithic and would have just basically implemented hard coding all the behaviors of what a network can do. So let's say the initial reference controller implementation by Stanford did only one thing, which was to make the data plane act as a series of learning switches. And maybe you also have a tool like, say, DPCTL that let you use OpenFlow manually to push in entries into the flow table. Current control platforms are a bit more flexible in that they're modular. In that you can just add new applications by developing different types of services as these modules or network applications, and they usually have some kind of a programmatic API or some kind of a command line interface, RESTful API. Some of them even have GUIs. But still, most of them are physically centralized for the most part. That largely comes from the fact that it's just easier to implement them and to push out implementations quickly. So of course, only having one single thing controlling a whole network has its drawbacks. A single controller can easily become a bottleneck or a point of failure. So if this one server goes down, the whole network might be out there just without a control plane. Even if you have a server that has great uptime, you might still be bottlenecked by the hardware limitations of the server itself. And even if you have a powerful server with great uptime, you might still have a very large network whose diameter is too large, so a switch might not get the configurations in time to actually handle traffic real time. So you might not get the flexibility. So OpenFlow networks try to compensate by having different, I guess, protocol implementations in some case, like say the OpenFlow roles, which give the control plane an ability to have multiple standbys, have a master and slave controller, make a failover smooth just in case the main controller goes down. You might also have switch configurations that let you point it to multiple different controllers just in case the first controller that it's connected to fails. You might be able to try another down the list. And finally, many controller implementations just use extensive parallelization, at least some amount of threading to be able to handle incoming control messages faster. So one of the first questions that was asked was, what if we can have multiple controllers in a control plane?
Question. So how many switches can a single controller control, or is there a limit in terms of the number of switches that a single controller can service?
It largely depends on the implementation.
But in production environments, what do you think that number is?
Production environment.
Is it 100? Is it 10? Is it 1,000?
It's probably into hundreds, I've
Okay.
heard of.
Okay.
If it's simulated, it can be far more.
If it is what?
If it's simulated, it can be far more as in
Okay.
benchmarks with the virtual switches. And I have a little bit of the results later on for at least Floodlight. One of the first experimental control planes that came up was the distributed control plane. You have multiple copies of a controller with the same services and a same network view, some kind of a synchronization mechanism just scattered throughout the control plane. So this is beneficial in that you can reduce the distance between any given switch and a controller that it can connect to. And because you have multiple controllers running simultaneously, there's hot standbys that kind of come in, like it kind of comes along for free. Not free per se, because there are still mechanisms that you need to to fail over. But it's much more easier to implement than a single controller mechanism. So it's scalable and resilient. But the problem with distributed control planes is that it's either highly experimental, so it's not really available even if it's open source, and the mature implementations are usually closed source production controllers, like say Google's Cardigan or Onyx. So it's not something that a researcher can just download and run and test out and develop on. And more to our point here, a distributed controller strives for uniformity. It tries to have all the controllers have a synchronized network state view, so they can, so any given controller can apply a change to the network and not have it conflict with anything else. That means that it'll still have to rely on different mechanisms if an administrator wants to, say, add another set of services to coexist on the same network. So there's different types of approaches here, like say network hypervisors that kind of treat each controller as, say, a virtual machine on a PC, giving it a different virtual network to act upon. There's also network compilers, so two different controllers can try to apply their changes to the network, but this compiler would verify that none of the configurations would conflict. Some of you even went to modifying the switches to return some of the intelligence back into the data plane, to have the data plane take some parts of the control plane functions. And there's finally highly specialized applications that make it possible for different types of networks to interface with each other. So one of the more well-known ones is SDN to TCP/IP network type applications. So this is where we want to introduce the concept of a heterogeneous control plane. We still have multiple controllers, except given two controllers from this control plane, they might host different services. We want to think of each controller as something that implements part of the network stack, or part of one or more network stacks, actually. And each controller basically communicates with one another through some kind of a control plane communication mechanism. So what would happen is, given that a event comes in from the data plane, different controllers might work on the same event. So the control plane can kind of pick and choose what kind of services are being executed, therefore letting different types of services to be mixed and matched to handle a certain event. So what I want to think of it as is a reformulation of different network stacks interacting in terms of different controllers interacting. So the structure of the control plane, I want to add another attribute, which is hierarchical. So basically, I'll have a group of controllers arranged in different tiers. The higher tiers would handle events that are more global scope to the network and less frequent. And because we have the tiers, we have these notions of client, servers, and peers. Basically, giving a tier, something above it is a server, and something below is a client. We make this distinction because each tier handles a certain set of events. Whatever it can't handle may be handled by a server. So that's where the client-server relation comes in. Each controller is connected to one another with these intercontroller links. These can be thought of as something joining together different pieces of a network stack. And this also allows the control plane to pick and choose and create routes for different events.
So I guess before you leave this diagram, so are you assuming that all the nodes in this in the control plane have the same network map topology, or is that not assumed?
No, that's not really the higher you are.
No, I mean, so if I'm trying to, so in the T0 data plane, I have some set of switches.
Yeah.
So do you assume that all the nodes in the different tiers know about all the switches in the data plane? Or is it partitioned, or you leave that resolved in this architecture?
So this kind of depends on two things. One is the service running on each of the controllers, but for the most part, I want to use the hierarchy to kind of handle all of the more frequent, more switch-oriented scope because of the lower tiers. So each of the tier 1 controllers might be attached to one switch and just focus on saving that one switch. And maybe higher up, they would just handle more network-wide type events. That's
Well, I
the
was trying to think of an example where, let's say I wanted to build some sort of like circuit switching using this architecture. So, you would tell A1 to maybe set some,
So,
set some of the rules in the switches, and then maybe send a message to A2 and then to A3, or would it go up
So-
and down, or?
in that case, one thing that might happen is, say, C1, which is connected to everything else indirectly through V2, would collect just large-scale topology information, and then use that to, say, instruct AS1 through 3 to push in certain types of messages to the switches to set up the circuit.
The initial routing path probably requires global information,
Yeah.
so you go up, but if you wanted to adjust the quality of service, for example, you can do that locally through A1.
So,
Okay.
oh, sorry.
Oh, no, go ahead.
One more.
Yes.
So, so the intuition behind arranging it hierarchically, what is it?
So basically, there's just different types of applications. Some things are invoked more frequently, like say, if a controller handles forwarding, it might have to handle a bunch of transient flows, so frequent packet-ins or frequent events. And there might be something else, like say a ACO that's only worried about new hosts entering the network, which is far less frequent and can happen at any switch. So the ACO would sit on the higher scope, kind of watching over everything, and the forwarding would kind of just focus on just an individual switch. That's kind of
Yeah. And so is this a logical organization or a physical organization? In other words, in data centers, typically switches are organized in 3 tiers to deal with traffic at the different scales, right? So you propose, when you realize this architecture, do you propose layering it on top of an existing data center architecture, or do you propose that this is more of a logical organization?
It can be either logical or physical, but I kind of assume that there needs to be a separate control plane network that's there, the network being like these interconnected controllers, so it's kind of like having a cluster of machines.
Okay.
So looking at the hierarchical structure, another way for it to be viewed is I have this like a traditional single controller with many different services, and I basically decompose it into different controllers that are organized in tiers depending on what kind of services demand what types of events. So if I had, say, authentication and forwarding, they might be separated into 2 tiers and 2 different classes of controller that handle different events. So there's many implications to trying to design this control plane. The controller becomes much more complicated. There needs to be some kind of a controller cooperation scheme. So there's going to have to be some kind of a processing chain that spans across multiple controllers. There also should be some way to select paths within the control plane to reach certain services, and some of them will be better than others. So there needs to be some kind of a routing mechanism to find optimal paths to different services. And finally, given a controller starts up in a control plane, it's going to need to be able to discover what services are available and what clients it has, what servers are there. So there needs to be a discovery mechanism as well, and an information propagation scheme. So ultimately, for the implementation, we ended up having controllers with these three main attributes. They're first recognized by two identifiers, a unique identifier specific to the controller itself, the UID, and one that describes the controller's capabilities or the services, which is the service ID. We use these two mappings because then it can be used in a similar way to having one as like a topology-based identifier and a service-based one. So we can create mappings like, say, the best route to reach a service of SID A would be through UID B, and create a routing table. You can also create a mapping like, say, this SID is tied to a service that handles these types of events, and create another type of mapping from that. And even if the route changes, because the SID and the UID are decoupled, the mappings can be built separately. Because there's also the intercontroller type of event handling, we also create a notion of a transaction for each event that's being handled in the control plane. Each event is given a unique transaction identifier, and that is used as a key to another context map that allows a controller to, say, track a different event and how it was processed.
So the transactions are valid across all these controllers, like the same transaction? Is that the idea?
Oh, yeah. Each controller has its local notion of that event's transaction.
But I could follow a chain. If a transaction had to go up the tree and then back down,
Yeah.
you have the same identifier.
And then it would just map and remap down and find the paths that it traveled through. So as an example, I'm taking the simple two-tier model that I had before. I'll call one controller 9 and the other one 10. So when a packet in comes from a switch, a packet in indicates that a switch could not find an action tied to a certain type of a packet header. So in this case, the switch might have had a new host attached to it and start trying to send traffic. The switch sends a packet in to the first controller, saying that there was a packet associated with this host with identifier A. This client controller first tries to classify this event. It finds that this event is a message type event, and it's associated with a new host that it does not have any knowledge of. And because its service, which is forwarding, cannot handle new hosts, it tries to find listeners that can handle these events. So it looks up what kind of services have the ability to handle new device events and pulls up this SID 30. It then tries to look up a next best hop to reach that service, which in this case will become 10. So when it finds that service, it would encapsulate that message in a control plane control message and send it to its server, which would be this controller with this UID of 10. It so happens that the controller 10 also holds the service with the ID 3. So it would handle the ACL lookup, find that the host is not allowed to transmit traffic on this network, and return a deny in the form of a OpenFlow, like a flow mod that would instruct the switch to drop the traffic that's associated with that host. This message would travel back down with the help of the transaction mappings and back to the original switch that it came from. So it does this. So a message would move up a tier if it can't be handled in the current tier, and move back down if there is a response associated with it.
So can you comment a little bit on that? Go back to that figure, so the convert and the split.
Oh, sorry, I completely forgot. Another attribute that's associated with a service is a certain type of client process chain behavior, like a type of a directive. So different services might want clients to behave in a different way in order for it to be able to act properly. So I do have like a small example kind of coming up later, but these are just client behavior configurations that the server might ask the client to uphold.
Question.
Yeah.
How do you get that SID3 from the first controller?
When the control plane network is initiated.
So which means on each controller there's a common database that stores like a service mapping to all available service on each controller?
That's one way that can be implemented. For this, there's different handshakes for exchanging this information that gets propagated down the throughout the
So
network.
there must be an control the communication protocol within the controller network.
Yes, there is.
Right.
So that's one of the many things that have to be implemented.
Yeah.
Okay, so to enable that kind of moving of events around in the control plane, there has to be some coordination scheme. So basically, a server directs a client to behave in a certain way so that it knows to pass certain types of events to it when it can't handle it. So these configurations are exchanged from server to client in configuration messages or subscription messages, and they contain information like, say, UUID of the controller, the server, and also things such as service ID, the events handled by that service with that service ID, and packet process chain behavior of the client. So that becomes important when there's applications that require a client to kind of behave in a very specific way. For example, the ACL might not want the client to continue processing and trying to forward the traffic before it knows whether the host can be allowed on the network or not. So it might ask the host to halt the client to halt processing while the server is still processing and evaluating whether the host is allowed on the network. And I call these behaviors directives. There's just 4 basic types. Deny and allow are like regular firewall policies. If it matches this type of event, drop it. If it matches this type of event, allow. And then there's divert and split, which is a block while the server is block until the server returns a result, and split would be continued processing as normal. And in addition to this process chain service information, service reachability information is also encoded in these packets. So that would be a route to a different type of service. So how many hops it takes to get to a certain service. These configuration messages are propagated down to the clients below once a client receives it from a server. So at each step, the hop count is incremented, so the controllers can collect these configuration messages and build up a least hop route to each of these services. And hop is just this simple metric that was just chosen for ease of implementation. So these configuration messages were exchanged during the handshake between the client and the server. It's basically a modified OpenFlow handshake, starting with a OpenFlow hello, and configuration request reply, somewhat like the features request and reply that's exchanged between a controller and a switch, except containing those aforementioned pieces of information. In addition to its own configuration reply, a controller might also send to a client previous configuration replies that it had received from the tiers above it. And these are sent in the form of these update messages. All of them are treated in the same way. Basically, they're used to build up these service maps, route tables, so on and so forth. And once that the mappings are complete, it goes into a steady state where these keep alive echo request reply messages are exchanged. So before I go into the details of the implementation itself, I just want to go over how a controller in general is constructed and kind of describe it in terms of this layered model. So looking at different types of source code from different controllers, it turns out that there's 3 major components to an OpenFlow controller. Starting from what's closest to the data plane, there's the control channel handler that sends and receives OpenFlow messages. Above that is the event dispatcher, which takes these messages and converts it to different kinds of events or signals that the controller can internally understand. And the dispatcher also distributes these events to its applications, which are basically the event handlers that handle these specific different types of events or return configurations to switches, so on and so forth. So looking at an example of the Floodlight SDN controller, we look at Floodlight because this was the platform that was used to implement this controller for this heterogeneous control plane. So it does cleanly separate into 3 of these layers. The black arrows show the flow of events through the 3 layers here. So the OpenFlow channel handler receives and sends OpenFlow messages. The core dispatcher is the ingress part of the dispatcher, which turns these messages into events. Each of these events are dispatched to various types of Floodlight modules, which might create topology mappings, which might behave as a firewall, and which might calculate routes for some kind of routing algorithm. And whenever one of these modules needs to configure a switch, they would write out through one of the egress dispatchers, which take the form of these different representations of the various network elements that the controller finds. So in this case, this controller is connected to these 3 switches, so it would have 3 of these egress dispatch entities. So switch 1, switch 2, and switch 3 over there. So events in specific to Floodlight, different controllers have different notions of what are events. In the case of Floodlight, it reflects the different kinds of events that happen in a data plane, so different state changes to the network, like say a switch connecting or disconnecting from the controller, or a device joining or leaving the network or changing its IP address or VLAN. And of course there's message type events, which are fired during when an OpenFlow message of a certain type is received. Everything is highly modular, everything's just Java modules. And there is this notion of a packet process chain within the controller itself for handling different types of events. So moving into the implementation of the hierarchical version of Floodlight, we extend the base Floodlight platform with various modules. They're the ones denoted in green over there. That includes the client and server channel handlers that let a controller connect to higher and lower tier controllers. Dispatch entities for clients and servers. And the remote dispatch module, which lets events be passed out to external controllers and remote connections. And of course, there's the different types of mappings, like the transactions and routing service ID to event. So the control messages themselves between the controllers are implemented using OpenFlow. We extended vendor data type, the vendor type message, which is specifically intended for modifying OpenFlow without breaking away from the specifications. And we also reuse standard message types like the echo, request, reply, and hello. We also extend the core dispatcher with the remote dispatcher to recognize additional events, like say certain types of packets that match certain TCP/IP header contents, different types of event triggers, which are certain packet-in messages that are associated with different events. Like, say, packet-in is associated with a new switch joining, or limited wildcarding, like, say, any device event. And finally, to have the controller be able to handle messages as something in this complicated control plane, we have 3 packet processing chains as opposed to the one in the base controller. So I'm going to kind of go over a brief overview of each of these control process chains. The first one is the client escalation. This is what does the service ID lookup, finding the next hop, moving the event from one tier to the tier above. These are color-coded in terms of the different colors that we use for the different layers. So the dark blue is the control channel, like the channel handler. It might be the client server or OpenFlow channel handler. In this case, it's either the OpenFlow handler or the client channel handler from a lower tier. This blue represents the dispatch, the remote dispatcher dispatch elements. It checks to see if the events can be handled locally. If not, find the next, the different types of services that might be able to. And that's taken care of by the applications, which are found in the light blue. The second process chain would be for moving events within a tier. So not all controllers in one tier might be connected to a controller above or below it, in which case it might have tier connections, which are horizontal connections within the tier that allow it to have events routed to another tier on behalf of the initial controller that wants the service from like a higher service. So this would start off in the client channel handler, and if it can process it itself, it'll try to push it to the local process chain, in which case this will be a server type function. If it cannot, it'll try to find the next hop that can reach the next tier above, which would be the peer function. And finally, there's the client return path, which is the translation of like the transaction identifiers to figure out where the original message came from and where the event should be handed down to. So this would go from the higher tier, from the server channel handler, to either the client or the OpenFlow channel handler to another tier below, or the data plane. So we did 2 major evaluations for this rough prototype implemented with Floodlight. So we focused on overhead and scalability. In specific, the overhead was measured in terms of event handling times, how long it took for a packet in to come out as a response, like say a packet out or a flow mod, and how the different types of process chains and how many hops there are in your route affect that processing time. And we looked at scalability in terms of the processing rate of the control plane, how many OpenFlow packets can it handle per given unit of time. And these tests were run on the Orbit sandboxes. We used these custom node images with this modified version of Floodlight and a handful of tools for taking these measurements. And each of the different nodes in the sandbox were either delegated a controller role or control plane, or some kind of an OpenFlow client role, which just generates OpenFlow messages to push into the control plane. So this is just a rough diagram. Each sandbox has 2 VLANs, so I just reuse those 2 VLANs for the purpose of control plane and data plane. So the red and purple there show the traffic getting pushed in from C1, which is the OpenFlow client, generating switch-like messages, to C2, which is the first tier of the control plane. And every other message from that controller onward gets passed through the control VLAN. So the first test that we did were with overhead measurements. So So basically took the time it took for a packet in to be processed by this one service that converts these packet ins into corresponding packet outs, which would instruct the switch to push out a packet through a certain port. The packet ins were generated using a custom client that just generated a bunch of random packet ins, and these packets were captured using TCP dump, and the timestamps were used to get an approximate measurement. 3 different scenarios were tested. The first one was multiple tiers, having many hops to get to a service, and the 2 different types of client directives that involve having the message be escalated to a server.
So packet in is when a switch sends a control message to the controller?
Yes.
Okay, and the packet out is when the controller returns the rule or whatever that the switch is going to use to forward. Okay, so that the time between that is basically the latency from when a switch gets some switch receives something that doesn't have a rule to when it can resolve.
So we want to minimize that time ideally. So for the first scenario with multiple tiers, just chain together up to 5 controllers, and just collect maybe like 10,000 samples, and kind of plotted it out as a distribution. So we see that that's not what it was. So it turns out link latency is the biggest source of overhead. Discounting that, the processing times per controller ends up being about 0.23 milliseconds. The latency comes from the transaction lookup, preservation, lookup of the next step, so on and so forth.
Question.
Yes.
You talked about the transaction time per controller, right? But this time is highly variable depending on how large is the network and how complicated is the applications. Could you provide more information on how you set up this simulation or emulation? How large is the network?
So I was using the testbed that was shown in this type of setup. Each of these boxes are actually a physical PC. They're all connected through an aggregate switch. So whenever there is one link, it's actually going through 2 links that are connected together by a switch.
So there are 11? I couldn't see that number.
This is just C1 through Cn, so n gets is variable depending on the measurements that I took. In this case, it would be C1 through C5.
C1 through C5.
So there will be
only 1 tier.
oh, sorry.
Is there only 1 tier here?
There's up to 5 tiers.
So the tier, the reverse line.
So each hop from C1 to C2 will be 1 tier, C2 to C3 will be the 2nd tier. And each tier is just purely just doing the routing mechanism, just lookup of SID next hop. Only the topmost controller in the highest tier would actually have this packet out generating service in this case.
So I think you could point out to answer his question, these numbers are not very sensitive to the network topology. They're sensitive to the processors used, which in this case are whatever, I don't know which machines you have, and their operating system and so on, whereas I think the actual switch topology will not influence this much.
Okay, that's interesting.
Well, only related to the processor of the controllers.
And on the actual lookup time, like if a controller in a certain tier needs to churn a lot of things in order to decide where to send that might increase the time. I guess in your case,
Oh,
it's
yeah.
a simple rule.
These are fairly simple, so this would be thought of as a lower bound, but you can speed this up like getting faster processes with, and what was the link speed here?
Yeah.
This was 1 gigabit.
Yeah, I have a question. So there seems to be a big lot of linearity there. So when you go from, if you're just going to a single controller, it's kind of in the hundredth of a millisecond. Well,
It's
tenth of a
about-
millisecond regime, and then all of a sudden you go to 2 controllers, you're out of the tenth of a millisecond to closer to a millisecond.
Um,
So do you have any idea? And then it looks linear from there. So I'm just wondering,
um,
where
These
that
values-
big jump between hops 1 and 2 lie.
So 1 and 2 is most likely the difference of having an actual service that's processing the packet being there or not. So with the baseline,
I think in the single tier case, you're back to the normal case. You're back to the everything's all in one box, and then you pay that overhead to get out of the box, and then after that, you increment the steps.
so there's 2 large time hits here with the service processing and actually the first initial lookup process of figuring out where the service is, creating this map, establishing this transaction.
So in the one hop case, you don't have any, you have a shortcut, which it's all in the same box, I can ignore all that stuff.
Yeah. So it's just going directly to its local packet processing, and which is actually fairly fast. And then there's the jump from the initial penalty, and then everything is basically
But I think you want to also point out that the purpose of you're paying a penalty latency, but you have processing scale that you're gaining, which was part of your motivation here. Now you can handle 10,000 requests per second instead of.
so in some sense.
Yeah, that's what I was going to ask something about that, because that's not quite visible here in terms of this presentation on the slide. There is this penalty you're paying, but then you have to have this great benefit to pull that out more carefully. Otherwise, why not just broaden your hardware configuration to keep it at tier 1?
If you have more state.
So look for that, looking for it.
Yeah, I'm getting to it. So there's 2 more of these kinds of tests. The second and third ones are for different types of server requests to the client. So this is possibly the worst case of having multiple servers that want the client to halt each time it's requesting, it's processing a request. In which case it still proportionally increases with the number of servers that are there. For this case, I should note that there's different topology, in which case I have 2 tiers. The first tier is this client controller, the second tier has the different numbers of servers that are processing the events that are being passed to it from the client. So in this case, each of these new curves shows a server creating, server processing this event, and also the client creating a new map or a new transaction type mapping for each, or recovering a previous state. And finally, there's the split directive, which is just to send a copy to the server above, which, as expected, takes the least amount of time because it's just firing off these requests to each server, and it only has to wait for the last server to respond for the time measurements. So the second test that we did was for scalability. So how much, given a bunch of packets coming in, what the processing time per packet is, and what the processing rate per packet is. We expect the first one to increase with a higher load because the CPU that's loaded takes more time to process things, and processing rate of the packets should drop as the controller starts dropping packets. We first tested out using a baseline stock controller, just a single Floodlight instance, and we stress it with the controller benchmarker called cbench. We emulate this highly active data plane with many virtual switches and virtually like many unique packet ends with different MAC addresses. To collect the statistics above, you call the packet monitor module, the performance monitor module, which is something that comes with this called Floodlight. And it turns out that because of the way that Floodlight is implemented, it behaves optimally when it has only 4 data paths to handle. And this has to do with how the threading was implemented for the channel handler. So this is a plot for different numbers of virtual switches to varying numbers of packet ends. You can see that there's this massive dip at 4 where it takes the least amount of time to handle each packet on average. And after that, it does go up as expected. And now I try to apply this same type of testing to a hierarchical scenario. I test out this 2-tier control plane. We have 2 tiers. The first tier has varying numbers of client controllers, 1, 2, or 4. And because we know that the optimal for Floodlight is 4 data paths, we fix each tier 1 controller to be connected to 4 data paths. And for tier 2, it's a server that just requests new device event triggers, so any packet in that's associated with a newly seen MAC address. So what's expected here is that because tier 2 is requesting only a subset of the events that are being pushed into the data plane, it's buffered from the breadth of the packet ends that are generated. And event handling capacity at tier 1 just corresponds to the number of controllers that are there. So even though we sacrifice processing times, we might actually be able to handle more packets. And you see that it's true in this case. The left graph shows the amounts of packets that are received from the process chain per unit of time according to the performance monitor. And the right shows processing time per packet for a tier 1 controller, just a single instance of a tier 2 controller. So you see that there is this big gap between tier 1 and tier 2, because tier 2 only has to deal with a subset of the events.
So I guess before, the previous bunch of slides was what you paid in terms of milliseconds for packet processing time, and this is what you gain. You gain a tier 2 that's relatively flat.
It's relatively buffered from everything else. And in terms of events that I can handle at the first tier, if I want more events to be handled, I can just add more controllers. But this comes with the caveat that the application that's running on those controllers can permit just a local scope handling of each switch. So this was just a very primitive preliminary implementation. So there's plenty of things that can be improved or investigated. So one thing is the hierarchy here in this implementation is somewhat hard-coded in that a configuration file is handed to a client, and the client is already given which servers it can connect to. So one thing that can happen is if we have multiple controllers that can send out discovery messages or use some kind of like a service ID resolution scheme, we can have a self-assembling hierarchy or topology. Another issue is control plane security. Right now there's very minimal means for authenticating these controllers that are joining the control plane. The most that it does is to see if whether a given controller is matched in terms of controller UID and the expected role it should have, whether if it's a client or a server or peer. So it works on a relatively lax trust system. So another bit of work that can be done is to actually secure this and to add some kind of mechanism to prevent rogue controllers from joining this hierarchy. There's also plenty in terms of application development. There's very few real examples of applications that can exploit or take advantage of this kind of hierarchical scheme where there's different types of network views and different types of events that are available to it. So one thing that can be investigated is what kind of applications can use this type of control plane the best. And with a more mature implementation, you can start to pull out different kinds of specifications that might be added back into maybe the OpenFlow specifications for controller interactions. Because that is actually not a very clear cut or defined thing defined in the protocol itself as of now. So my conclusion is just 2 points. So this hierarchical heterogeneous control plane, it does have reasonable amounts of overhead processing time, even though it does take a penalty hit compared to a single controller instance. But it does compensate by being able to handle more requests that are incoming, so it can scale out in a much better way. And we're able to implement this with Floodlight, which is this open SDN platform, which kind of gives you like a proof of concept of how open SDN kind of promotes development of different types of experimental network technologies. So those were the 2 main things that kind of came through. And that is the presentation.